Right now, somewhere in a laboratory in the United States, a battery is being charged using nothing but iron, water, and air. It costs a fraction of what lithium costs to produce. It does not catch fire. It does not require mining operations in war zones. It does not degrade after a few hundred charge cycles. And the active material at its core is something you have been scraping off old pipes and throwing in the trash for your entire life. It's rust, literally iron oxide. The same reddish-brown flaking residue that destroys cars, bridges, and garden tools. And the engineers who figured out how to turn it into a viable grid-scale battery are now threatening to make lithium-ion technology look like a very expensive detour. So if this technology is real, and the test data says it absolutely is, why have you not heard of it? And should lithium investors be worried? Let's find out. Before we go any further, if you are finding this useful, hit like and subscribe to Lost Tech Vault. We dig up the engineering breakthroughs that the mainstream tech conversation consistently buries. And this one might be the most consequential we have ever covered. To understand why rust batteries matter, you first need to understand what's wrong with the batteries we already have. Lithium-ion technology has dominated portable and grid-scale energy storage for the past 3 decades because it does something no previous battery chemistry could do as well. It packs an enormous amount of energy into a very small, very light package. That energy density is why your phone does not weigh 5 pounds and why electric vehicles can travel hundreds of miles on a single charge. But lithium-ion comes with a set of structural problems that the industry has known about for years and quietly managed rather than solved. Lithium is not abundant. It is concentrated in a small number of deposits, primarily in Chile, Argentina, Australia, and increasingly contested regions of Africa and Central Asia. As electric vehicle adoption scales globally, demand for lithium is projected to increase by as much as 4,000% by 2040, according to analysis from the World Bank. The supply chain simply cannot expand fast enough to match that demand without dramatic price increases. Then there is the thermal runaway problem. Lithium-ion cells store energy in a chemically volatile state. Under the right conditions, a manufacturing defect, physical damage, overcharging, or extreme heat can trigger that stored energy to release catastrophically. This is why lithium battery fires are so difficult to extinguish. The cell generates its own oxygen as it burns. Water does not stop it, you just have to contain it and let it exhaust itself. And finally, there is cycle degradation. A lithium-ion battery loses a measurable percentage of its capacity with every charge and discharge cycle. After 500 to 1,000 cycles, depending on chemistry and usage, the cell is operating at a fraction of its original capacity. For grid-scale storage, where a battery might cycle once or twice every single day, this means replacing the entire installation within a few years. These are not minor inconveniences, they are fundamental constraints baked into the chemistry. And they're exactly the constraints that iron-air battery technology was designed to eliminate. The concept of using iron as a battery electrode actually predates lithium-ion by nearly a century. Thomas Edison himself filed patents for an iron-nickel battery in 1901, intending it as a power source for early electric vehicles. Edison's design worked, but it had a critical flaw. It was slow to charge and had lower energy density than the lead-acid batteries of the era. The technology was shelved and iron batteries largely disappeared from mainstream engineering attention for the better part of 100 years. What brought them back was a question that grid operators started asking loudly around 2015. If we are going to run an electrical grid on solar and wind, which only generate power when the sun is shining and the wind is blowing, we need to store that energy for hours or even days at a time. Lithium-ion can do this, but at a cost that makes long-duration grid storage economically prohibitive. The target price for grid-scale, long-duration storage that would make renewable energy fully dispatchable is approximately $20 per kilowatt-hour of stored energy. Lithium-ion, even at its most optimistic projected costs, is unlikely to fall below $60 per kilowatt-hour at the system level. Iron-air batteries, according to a peer-reviewed analysis published in Energy and Environmental Science, have a theoretical cost floor below $20 per kilowatt-hour. Some projections put practical manufacturing costs as low as $6 per kilowatt-hour at scale. The reason is almost insultingly simple. Iron is the fourth most abundant element in the Earth's crust. It is already mined in staggering quantities for the steel industry. Its supply chain is mature, distributed, and cheap. And the core electrochemical reaction that makes the iron-air battery work requires no exotic materials, no rare earth elements, and no cobalt, a material whose mining has been linked to severe humanitarian abuses in the Democratic Republic of Congo. Here is how the chemistry actually works, and it is genuinely elegant. An iron-air battery operates through a reversible rusting process. During discharge, when the battery is releasing energy, iron at the anode reacts with oxygen drawn in from the surrounding air. Iron atoms lose electrons. Those electrons flow through an external circuit to power whatever load is connected, and the iron at the anode oxidizes. It rusts. During charging, the process runs in reverse. An electrical current strips the oxygen back off the iron oxide, regenerates metallic iron, and releases oxygen back into the air. The electrolyte is a water-based solution. The cathode is essentially a permeable membrane that manages the airflow in and out of the cell. No sealed pressurized containers, no flammable organic solvents, no thermal runaway pathway. Form Energy, the Massachusetts-based startup backed by Bill Gates' Breakthrough Energy Ventures and steelmaker ArcelorMittal, has already built demonstration systems at this scale. Their published performance targets call for a 100-hour discharge duration, meaning a fully charged installation could power a load continuously for more than 4 days without any new energy input. Lithium-ion systems, by comparison, are typically optimized for 4 hours of discharge. Independent testing of Form Energy's pilot installations, reported in MIT Technology Review, confirmed stable cycling performance across hundreds of charge-discharge cycles with minimal capacity degradation. The cells showed no thermal events under any tested condition. So why isn't this already replacing lithium everywhere? The honest answer is energy density, and it matters for some applications more than others. Iron-air batteries store roughly 1/10 the energy per kilogram that lithium-ion cells do. For a stationary installation bolted to the ground next to a solar farm, this is largely irrelevant. You just need more physical space and more cells, and because the cells are so cheap, the economics still work dramatically in iron-air's favor. But for an electric vehicle where every kilogram of battery weight directly reduces range, iron-air's low energy density is a disqualifying limitation. You simply cannot build a practical electric vehicle around a battery chemistry that requires 10 times the mass of lithium to store the same energy. For transportation, lithium-ion or its successors like solid-state lithium will remain dominant. The disruption iron-air technology threatens is specifically to stationary grid storage, which is itself a multi-trillion-dollar market as the world transitions to renewable generation. Every large solar installation, every offshore wind farm, every grid substation in a region targeting carbon neutrality needs long-duration storage. And that is precisely the market where lithium-ion is weakest and iron-air is strongest. Form Energy has already announced a commercial manufacturing agreement and is targeting initial grid deployments within the next few years. Several utility companies, including Georgia Power, have signed letters of intent for installations. What we are watching in real time is a technology that was invented over a century ago, abandoned for reasons of competitive disadvantage rather than fundamental failure, quietly resurrected by engineers who asked the right question, and now positioned to play a central role in one of the largest infrastructure transitions in human history. Iron doesn't burn. Iron doesn't run out. Iron doesn't require a mining operation in a conflict zone. And iron has been rusting since the first time oxygen appeared in Earth's atmosphere. The engineers who figured out how to make that process useful and reversible may have just built the most important battery the world has never heard of. If you want to understand the other buried technologies being quietly revived to solve modern energy problems, subscribe to Lost Tech Vault. Watch our next video on the heat pump technology that was invented in the 1850s and is now making gas furnaces obsolete.